Okay, morning, folks. We're going to now enter into the last bit of the binomial theorem. Right here, this is a case, we're looking at the case when the power n in 1 plus x to the n, when n is not a positive integer. Okay, I've already set up a couple of main points here, so let's go through them. When n is not a positive integer, the binomial theorem, and thus the series expansion, is still valid, but it's only valid for 1 plus x to the n and not a plus x to the n. A must be 1. A must be 1. Okay, that's the first main point. You can only use the binomial theorem to expand 1 plus x to the n when n is not a positive integer. The next main point here, the series expansion is infinite. That's interesting. If you were to compare it with when n was a positive integer, the number of terms in the expansion was 1 more than the value of n. So for n equal 10, you had 11 terms in the expansion. N equal 15, 16 terms in the expansion, and so on. When n is not a positive integer, when n is like a half or minus 2/3, or some other number other than a positive integer, the series expansion is an infinite series. Which is why earlier on we were discussing that in many cases you only need the first few terms of the expansion. Because clearly in the case when n is not a positive integer, you would not be able to get the entire series expansion. So there, when n is not a positive integer, the series expansion is infinite. Next, the series expansion is valid for x, the modulus of x being less than 1, which translates into x being between minus 1 and 1. By the way, x is whatever term appears here in 1 plus x to the n, right there. So that could be, let's say, 1 plus x upon 2, or x upon some other number. Then that expression that represents x, the modulus of that expression will be less than 1. We'll get to examples with that a little later. Okay, so the expansion is only valid for the modulus of x being less than 1 or x being between minus 1 and 1. Compare that with when n was a positive integer. Excuse me. What's the difference? The difference is, in that case, the series expansion was valid for all values of x belonging to the set of real numbers. So when n is not a positive integer, the series expansion is a little more restrictive. You're only allowed to expand this series for x between for the modulus of x being less than 1. X being whatever term appears after the 1 in 1 plus x to the n. Okay. Well, what does the actual series expansion look like? Does it look similar to the expressions we had when n was a positive integer? Not really, though it's kind of related. Here's what it looks like. 1 plus x to the n is equal to 1. If I can get this pen to write, that would be nice. 1 plus nx plus n into n minus 1 upon 2 factorial times x squared plus n into n minus 1 into n minus 2 upon 3 factorial times x cubed plus, I'll do a couple more. Yeah, plus n into n minus 1 into n minus 2 into n minus 3 upon 4 factorial times x to the 4th. You can see the pattern there, and so on and so forth. And this goes on and on. The general term looks like this. N into n minus 1 into n minus 2 ellipses into n minus r plus 1 upon r factorial times x to the r, and then on to infinity. It's an infinite series expansion. That entire expression up there represents the binomial series expansion, or the way you apply the binomial theorem when n is not a positive integer. Looks a bit different from that NCR business when n was a positive integer, doesn't it? It's kind of related. Okay. So far, so good. Now, remember earlier I was saying the series expansion is valid only for 1 plus x to the n. Well, suppose you wanted to expand a plus x to the n. If you wanted to expand a plus x to the n, you must first rewrite it as a to the n into 1 plus x upon a to the n. So let's see. That algebra should not be beyond u upper sixes, but I'll go through it. If I started out with, let's say, just a plus x, like that, and I wanted to factor out a, then that would be a into 1 plus x upon a. That should be pretty straightforward. Therefore, if I raise the left-hand side to the power n, I must also raise the right-hand side to the power n. Laws of indices, I can split that into two parts. You get a to the n times 1 plus x upon a to the power n. And then what we do, we apply the binomial theorem or the binomial series expansion to this part. And when we are finished, we multiply the result by the a to the n. Multiply that into the expansion. But the expansion can only be performed on 1 plus x to the n, in this case 1 plus x upon a to the n. And of course, because x upon a replaced x, then the series expansion is valid for the modulus of x upon a less than 1. Let me pull that up. Yes, it's valid for the modulus of x upon a being less than 1, which can translate into x upon a being between minus 1 and 1. And if I multiply throughout by a, I will get x being between minus a and a. Notice there are no equal signs in that inequality. It's greater than minus a and less than a. No greater than or equal to or less than or equal to. There is no equal sign. Okay, those are the main points for the use of the binomial theorem, and hence the binomial series expansion when n is not a positive integer. Let's jump into some examples. Okay, expand each of the following in ascending powers of x. By the way, you can only, in this case, you can only get ascending powers of x for obvious reasons, right? The series expansion is infinite, so there's no way you can get to the infinite end to write the series going back the other way. All right, expand each of the following in ascending powers of x up to and including the term in x cubed. Also state the range of values of x for which the expansion is valid. And I gave 3 examples there. I'm going to go through them one at a time. 1 plus the square root of 1 plus 2x can be rewritten as 1 plus 2x to the power a half. And clearly you can see that's in the form 1 plus x, big X, to the power n. X in this case is represented by 2x. So we can clearly use the binomial theorem. Now they said expand each up to the and including the term in x cubed. So no problem. We'll simply write out the binomial theorem, the generic expression, and you should get accustomed to doing that. In general, 1 plus x to the power n is equal to 1 plus nx plus n into n minus 1 upon 2 factorial times x squared plus n into n minus 1 into n minus 2 upon 3 factorial times x cubed. I actually want to expand a second there. I actually want to expand 1 plus 2x to the power of a half. Therefore, I have to replace x with the 2x and also replace n with a half. So, no big deal there. If I did that, I will get 1 plus 2x to the power of a half is equal to, okay, first term in the expansion is 1. Let's try again. 1 plus nx, that would be a half. N is a half. X is replaced by 2x. Plus a half into a half minus 1 is minus a half upon 2 factorial times 2x all squared. Plus a half into a half minus 1, that's minus a half. Half minus 2, that's minus 3 halves. Upon 3 factorial times 2x all cubed. Mercy, watch fraction there, bye. I should leave it here for y'all to finish. Let me finish it up. 1 plus 2x to the half is equal to 1. The half times 2x, that should give me just x. Let's see here. A half times minus a half, that's minus a quarter. Divide by 2 factorial, that's minus 1/8. The 2 in the 2x all squared going to come out as 4. 4 times minus 1/8, that's minus a half. I think I'm right. Minus a half all squared. Minus a half times x squared, like that, sorry. The next one is, mercy. Gotta do a little side work in here, bye. First of all, that's going to be a positive. I have 2 minuses there. When I multiply, I get a plus. Good. I have 3 on top. I have 2 2's, 4 2's, 8 on the bottom. And also with 3 factorial. 3 factorial is 3 times 2. And coming out of the 2 cubed, that's 8 as well. Mercy. 8 goes out with 8. 3 goes out with 3. And it looks like it just leaves me with a half. What do you know? So plus a half x cubed plus yada yada yada. Plus minus plus. I only have 1 plus 2x, right? 1 plus 2x. Yeah, that one gave me a minus. And that one give me back a plus. Next one, yeah, the sign's going to alternate after that. Please double check my arithmetic there. But I think I'm right. And that's the end of that one. Right. Okay, so now, I have to give the set of values of x for which the expansion is valid. So I have to look back here. Oops. I have to look back here and see what follows the 1. The series expansion is valid for the modulus of 2x being less than 1, which makes 2x be between minus 1 and 1, which makes x be between minus a half and a half. So there, you can only plug values of x between minus a half and a half into that series expansion. That is why this portion is so important. Only values of x in that range would be valid values to substitute for x. Good. 1 upon 2 minus x is the next one. Let me move it down slightly. Okay. 1 upon 2 minus x is the next one. How do I get a binomial series expansion for that? Okay. Well, I can throw the 2 minus x to the top, but I prefer to factor the 2 while it's in the denominator first. So this will be 1 upon 2 into 1 minus x upon 2, like that. I think that's right. Yeah, that's right. And then just throw the 1 minus x upon 2 up into the numerator. So this becomes a half on the outside and 1 minus x upon 2 to the minus 1 on the inside. Well, that I've thrown up into the numerator. If I'd gone the other route first, which is to just throw the 2 minus x up first, 2 minus x goes up to the minus 1. And then it'll be 2 to the minus 1 into 1 minus x upon 2 to the minus 1. But then I'll still have to throw the 2 to the minus 1 back into the denominator to make it a half in front. So either way, I'll keep what I started with there. And of course, now I have to apply the binomial theorem to this portion. Binomial theorem or binomial series expansion. Because the first term has been converted to a 1. I can't stress that enough. When n is not a positive integer, and it's not, the power n here is minus 1. That's clearly not a positive integer. When n is not a positive integer, the series expansion is only valid when the first term of that binomial is a 1. Okay. So let's run with this one. Again, you start off by saying, just quoting the expression, in general, 1 plus x to the power n can be written as 1 plus nx plus n into n minus 1 upon 2 factorial times x squared n into n minus 1 into n minus 2 upon 3 factorial times x cubed. That's where the instructions say to stop. And I would like to expand the 1 minus x upon 2 to the power minus 1. And therefore I have to replace n with minus 1. And of course x with minus x upon 2. If I did that, I'll get 1 minus x upon 2. Yes, 1 minus x upon 2 to the minus 1 is equal to 1 plus the n is minus 1 minus 1 times minus x upon 2, mercy, plus minus 1 minus 1 minus 1 is minus 2 upon 2 factorial times minus x upon 2 all squared plus minus 1 times minus 2 times minus 1 minus 2 is minus 3. Oops. Minus 3. All upon 3 factorial times. I leave myself any space there, man. Cha. Pull you over a little bit. There we go. Yes. Minus 1 times minus 2 times minus 3 upon 3 factorial times minus x upon 2 all cubed. Let's see if you can simplify that. 1 minus x upon 2 to the minus 1 is equal to 1. Minus minus gives me a plus there, so this is plus a half x. Minus and a minus is a plus, and minus squared is also a plus. So everything there is a plus. The 2 upon 2 factor will shock out, and I'm left with a quarter x squared. Yeah, I can double check my arithmetic there again. Quarter x squared. The minus 1, minus 2, and minus 3 is minus 6. 3 factorial is also 6. So that leaves me with a minus 1 in front. The minus x upon 2 all cubed gives me a minus x upon 8. So finally I get plus 1/8 x cubed. That's a minus, plus, all the front chalk out, and I'm just left with 1/8. Again, I think I'm right there. But I'm not quite finished. Remember, I'm supposed to be expanding 1 upon 2 minus x, which was a half into this. So a half into 1 minus x upon 2 to the minus 1 is a half into the expansion. 1 plus a half x plus a quarter x squared plus 1/8 x cubed. There. I'll rewrite the left-hand side in its original format. If I rewrite the left-hand side the way it was originally written, 1 upon 2 minus x. 1 upon 2 minus x is now therefore a half plus 1/4 x plus 1/8 x squared plus 1/16 x cubed. Yeah, and that's the series expansion. Okay, what's the set of values of x for which the expansion is valid? I have to come back here where I did the expansion and take the minus x upon 2. The series expansion is valid for the modulus of minus x upon 2 being less than 1. Modulus of a negative is the same as the modulus of a positive, which means the modulus of x upon 2 must be less than 1, which means that x upon 2 must be between minus 1 and 1. And if I multiply through by 2, I will get x being between minus 2 and 2. I'm only allowed to plug values of x into that expansion between minus 2 and 2. Yes. Okay. That's not too bad. All right. A couple more examples. I'm going to go through them all because you got a nice little worksheet at the end of this. This next problem here is an interesting one. How are we going to do this? Okay. Find the binomial series expansion for that guy right there. Okay. So let's tackle it. There are actually a couple of good ways we can do this. I'm going to first go hard and fast by just throwing the two denominators up into the numerator. So I'll end up here with I'll end up here with 5 into 1 plus 3x to the minus 1 times 1 minus 2x, all to the minus 1 as well. And then I'll find the binomial. Notice each bracket has a 1 in front, 1 plus 3x and 1 minus 2x. So I can go directly and find the binomial series expansion for this, find the binomial series expansion for that, and then multiply the two series expansions and then multiply by 5. That's a reasonable way to do it. So let's check. I'll call this method 1. Okay. So let's go. And I'm supposed to expand the entire thing up to x cubed, which means I have to expand each bracket up to and including the term in x cubed. So when I multiply the two brackets, now I'll throw away anything that has a power higher than x cubed. We know that 1 plus x to the power n is equal to 1 plus nx plus n into n minus 1 upon 2 factorial times x squared, n into n minus 1 into n minus 2 upon 3 factorial x cubed, like so. Okay, so the first case, let's see what happens. So this becomes 1 plus 3x to the power minus 1 is equal to 1 plus minus 1 times x is replaced with 3x. My handwriting look decent, man. My handwriting is decent, right? No, plenty are gonna say no. Yes, plus minus 1 times minus 2 upon 2 factorial times 3x all squared plus minus 1 times minus 2 times minus 3. Right, minus 1, minus 2, minus 3 upon 3 factorial times 3x all cubed. 3x all cubed. Okay, let's tidy that up. 1 plus 3x to the minus 1 becomes 1 minus 3x. This is 2 upon 2 factorial, that goes to 0. 3 squared is 9, plus 9x squared. That's, ooh. So it's plus, minus, plus. The next one is minus. That's minus 6 upon 3 factorial, which is a minus 1. So that's minus from there, 27. Minus 27 x cubed. And that's the expansion for 1 plus 3x to the minus 1. 1 minus 3x plus 9x squared minus 27x cubed. Okay, let's do the other one. Let's do the next. Oh, maybe at this point we should probably find the set of values of x for which this first expansion is valid. This expansion is valid for the modulus of 3x less than 1. Y'all get the hang of this by now. 3x is between minus 1 and 1, which makes x between minus a third and a third. Okay, let's do the next one. To expand, and this time we are expanding what? We are expanding 1 minus 2x to the minus 1. To expand 1 minus 2x to the minus 1, what are we substituting or replacing? Replace n with minus 1 again, and replace x with minus 2x this time. If I did that, 1 minus 2x to the minus 1 will give me, I'm using the same general expansion up there, right? No need to write it back again. It's the same expansion I'm using, except I'm substituting different, well, certainly a different expression for x in there. So this is 1 minus 1 plus, sorry, minus 1 times minus 2x plus minus 1 times minus 2 upon 2 factorial times minus 2x all squared, and then plus minus 1 times minus 2 times minus 3 upon 3 factorial times minus 2x all cubed. Minus 2x all cubed. Barely fit. There. Okay. Let me tidy that up. 1 minus 2x to the minus 1 is equal to 1 plus 2x. That's a plus. That next one is also a plus. That'll be plus 1 in front and plus 4x squared. Plus 4x squared. It's a minus and minus and minus with a minus. Minus 2 cubed is also a minus. Minus and minus is a plus. So minus 1 out front times minus 8x cubed is plus 8x cubed. There. Plus that. Okay. And now we have to find the set of values of x for which this expansion is valid. The expansion is valid for the modulus of minus 2x being less than 1, which implies that modulus of 2x is less than 1, which implies that 2x is between minus 1 and 1, which implies that x is between minus a half and a half. Okay, so let me mark off the important parts here. I got the first expansion up here. And the range of values of x for which that expansion is valid. I have the second expansion down there, 1 minus 2x to the minus 1, 1 plus 2x plus 8x plus 4x squared plus 8x cubed. There it is. And I got the set of values of x for which that one is valid. Okay. So how do I get the overall expansion? Well, remember, give me a minute, let me create some space here. Remember, the original expression, 5 upon 1 plus 3x into 1 minus 2x, was rewritten as 5 upon 1 plus 3x times 1 minus 2x. Was rewritten as 5 into 1 plus 3x to the minus 1 times 1 minus 2x to the minus 1. So what we have to do is to multiply 5 by the expansion for the first one by the expansion for the second one. So that's now equal to 5 into the first expansion is 1 minus 3x plus 9x squared, 1 minus 3x plus 9x squared minus 27x cubed, times the other expansion, which is 1 plus 2x plus 4x squared plus 8x cubed. Like so. What I'll do, I'll multiply the first two brackets, and then the result, I'll multiply that by 5. So let's see. This becomes 5 into... Okay, here's the way I'm going to do this. Multiply the 1 by everything up to and including the term. Multiply everything in the first bracket by everything in the second bracket. And if I get a term that exceeds x cubed, I'll just ignore it. Just throw it away. At the end of the day, the overall expansion was required for all terms up to and including the term in x cubed. Anything exceeding that, we can throw away. So, 1 by everything in this 1 in the first bracket by everything in the second bracket gives me 1 plus 2x plus 4x squared. Oops, I'm to you. Yes, 1 plus 2x plus 4x squared plus 8x cubed. And then the minus 3x by everything up to determine x cubed. Minus 3x by 1 gives me minus 3x. Minus 3x by 2x gives me minus 6x squared. Minus 3x by 4x squared gives me minus 12x cubed. Obviously, the minus 3x by the 8x cubed would have given me something in x to the fourth, which I'm not interested in. Then take the 9x squared now. 9x squared by 1 gives me 9x squared, a positive 9x squared. 9x squared by 2x gives me 18x cubed. I don't need anything above that. Anything else would be in terms of x to the fourth and x to the fifth. And then the minus 27x cubed by 1 gives me minus 27x cubed. There. I still have a 5 on the outside. All of this times 5. So finally, 5 upon 1 plus 3x times 1 minus 2x will give me, let's see, adding everything in the brackets, that's a 1. By the 5 outside, that's a 5. 2x minus 3x is minus x. Minus x by 5 is minus 5x. Let me see, 9 and 4 is 13, minus 6 is 7. 7 5 is 35. 35x squared, that's a plus 35x squared. Ooh, I can't add now. 18 and 8. Hey, I can do this. 18 minus 12 is 6. 6 and 8 is 14. 14 minus 2 is 7. Oh, my arithmetic gone to the dogs. Gives me 13x cubed, and 13 5s is 65. But that's a minus, right? Yes, minus 65 x cubed. Please double check my arithmetic there. So, interesting. That is the binomial series expansion for 5 upon 1 plus 3x times 1 minus 2x up to and including the term in x cubed. Now, not quite finished. What is the set of values of x for which this entire thing is valid? We know the set of values of x for which 1 plus 3x to the minus 1 is valid. And we know the set of values of x for which 1 minus 2x to the minus 1 is valid. But what's the set of values of x for which the entire series expansion is valid? Should I take the bigger range, the smaller range, the overlapping range? Well, let's see. Let's put it on a number line. What was the first one? For the 1 plus 3x to the minus 1, the series expansion was valid for x between minus a third and a third. And for the 1 minus 2x to the minus 1, the series expansion was valid for x between minus a half and a half. Let's put that on a number line and see where we end up. I could draw a number line. I don't even know what a number line is. There. This is, let's say this is 0. A third is obviously smaller than a half. So I put a half, minus a half and a half there and there. I'm not including the minus a half, and I'm not including the half, so I gotta put open circles. Remember that? Remember all them details? So, first one is valid. So within there, well, actually the second one, right? Yeah, no matter which one I do first. And then the minus 1/3 and 1/3. I'll bring this one down. This one is valid for within here. This is a third, minus a third, and this is a third. So, what set of values would both expansion be valid for simultaneously? Well, it's obvious where the two ranges overlap. In this region there. There. Common range of overlap. Right? If you pick any number between, let's say, oh, forgot to put in this half. If you pick any number between a third and a half, somewhere there, that's only going to satisfy one expansion, not both. So you have to pick the set of values that satisfies both expansions. And clearly that's between minus a half and a half. So I'll conclude this by saying for 5 upon 1 plus 3x times 1 minus 2x series expansion is valid for x between minus a third and a third. It must be ready to overlap. Where the series expansion itself was 5 minus 5x plus 35x squared, and then minus 65x cubed. So this is a perfectly valid way to do this problem. Does anyone see another way we can do this before I say? Obviously, I talking to me. You gotta answer to yourself. I don't like this. I prefer when you're in class. So quiz you properly. Yes. Is there another way we could have done this? Well, how about your partial fractions? Could we have used partial fractions? And the answer is yes. Method 2. So, the 5 upon 1 plus 3x times 1 minus 2x could have been rewritten as some a upon 1 plus 3x plus some b upon 1 minus 2x. I'm going to leave that part for you to do. Find the partial fractions. But I've already done it. So you can confirm for me that your partial fractions ended up being 3 upon 1 plus 3x plus 2 upon 1 minus 2x. Now, why is this a good method to use? Well, because I can still throw up the denominators. This becomes 3 times 1 plus 3x, and then plus 2 times 1 minus 2x. Oops, both to the minus 1. And then I find the binomial series expansion for this guy, and then for this guy. Multiply the first one by 3, multiply the second one by 2, and then add the two series expansions. Let's see how that goes. Obviously, I've already found the series expansions above, so it's not like I'm going to do them again. Right? So let's see. This becomes 3 into the series expansion for 1 plus 3x to the minus 1 was 1 minus 3x plus 9x squared minus 27x cubed. And the series expansion for the other one, 1 minus 2x to the minus 1, was 1 plus 2x, 2x, plus 4x squared, plus 8x cubed. So let's see what happens when we open out the brackets. And the difference here is that you add the two parts instead of having to multiply them and throw away extra terms. There's nothing to throw away here. This becomes 3 minus 9x squared plus 3 minus 9x, plus 27x cubed. I'm losing it. 27x squared. And 27 threes is 54. I think 27 threes is, I'm embarrassed. 27 times 3 is 81. Oh my goodness. Better not talk too hard. Yes, minus 81x to the x cubed. There we go. And then in the next bracket, we have 2 plus 4x plus 8x squared plus 16x cubed. So let's see if we can add the like terms here. This becomes 3 and 2, that's 5. Minus 9x plus 4x is minus 5x. 27 plus 8 is plus 35. And minus 81 plus 16. Minus 81 plus 16 is equal to minus 65 x cubed. So, now obviously if you were using this method on its own, then you would have to go about and expand, do the binomial series expansion for the 1 plus 3x to the minus 1 and the 1 minus 2x to the minus 1. But I had already gotten those series expansions from the first method, so there is no need for me to do them over. And of course, same again, you have to look to see where the two ranges overlap, and the series expansion is valid for x being between minus a third and a third. Right? Common range of overlap for the two expansions. So you need to confirm that the partial fractions are what I suggested they are up there. Give you a little bit of revision on your partial fractions. Let's try one more problem. This one is we're using the binomial theorem to find approximations. So here it is. By substituting x equal 1/10 into 1 minus x to the minus a half and its binomial expansion, find an approximation for root 10 correct to 6 significant figures. All right, notice they didn't tell us how far to expand. Now they want the answer correct to 6 significant figures. Root 10 is 3 point something. Even if I punch in the actual number in the calculator first, just to get a handle for what I'm supposed to end up with. Root 10 is 3.162277766. So 6 significant figures means 5 decimal places because the first significant digit appeared before the decimal point. All right, so basically I'm trying to figure out how far I should expand. I wasn't given instructions as to how far to expand. I know I'm substituting x equal 1/10 or 0.1. So let's say I expand to the term in x to the 5th. If I take 0.1 and raise it to the power 1/10 is 0.1, right? If I take 0.1 and raise it to the power 5, I get 1, 2, 3, 4. I get 4 decimal places. I get an extra decimal point. So if I take 0.1 and raise it to the power 6, I'll get 5 decimal. 1, 2, 3, 4, 5. I think I have to go deep into this thing, you know. Let me see. 1, 2, 3, 4, 5. I might have to go up to the power 7. Because I still have to multiply by a coefficient in front. Now the coefficient will be a fraction. Yeah, the coefficient will be a fraction, so it'll make it even smaller. 1, 2, 3, 4, 5, 6. I'm gonna go up to the term in x to the 7th. I might not need it, but I'll do it anyway. All right, so let's go. In general, 1 plus x to the n is equal to 1 plus nx plus n into n minus 1 upon 2 factorial x squared, n into n minus 1 into n minus 2 upon 3 factorial x cubed, plus n into n minus 1 into n minus 2 into n minus 3 upon 4 factorial x to the 4th. That's 4. I'll go up to the term x to the 5th. I don't think I need more than that. N into n minus 1 into n minus 2 into n minus 3 into n minus 4 upon 5 factorial x to the 5th. All right, so let's see. I actually want to expand 1 minus x to the minus a half. To expand 1 minus x to the minus a half, I replace n with minus a half and x with minus x. So therefore, 1 minus x to the minus a half. Yeah, but anyway, let's see what happens. Will give me, let's go 1 plus a minus 1 times a minus x plus a minus 1 times a minus 2 upon 2 factorial. Oh, I get new. Nothing in front. Minus 1 times minus 2 upon 2 factorial x times minus x all squared, plus a minus 1 times a minus 2 times a minus 3 upon 3 factorial times minus x all cubed, plus minus 1 times minus 2 times minus 3 times minus 4 upon 4 factorial times minus x to the 4th. And then plus minus 1 times minus 2 times minus 3 times minus 4 times minus 5 upon 5 factorial times minus x to the 5th. 0.1 to the 5th. I still think I need more terms, you know. I'm going to take 2 more. I just have a feeling I'll need more. And instead of figuring that out after the fact, if I don't need them, that's okay. 1, and then the next one is plus minus 1, minus 2, minus 3, minus 4, minus 5, minus 6 upon 6 factorial times minus x to the 6th. And then minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7 7 factorial x to the 7. 1 minus x to the minus a half is equal to 1 plus x. The minus 1 by minus 2 upon 2 factorial, that just gives me 1. In fact, all them coefficients in front would either give me a 1 or a minus 1, I think. So this is 1 minus x all squared is just x squared. The next one, that's a minus 1 times minus x cubed. That's just plus x cubed. Oh, wow. The next one is 4. That's plus x to the 4th, plus x to the 5th, plus x to the 6th, plus x to the 7th. What do you know? Yeah, this last piece here should have been minus x all to the 7th. 1, 2, 3, 4, 5, 6, 7. It'll give me a minus, and a minus x to the 7 is a minus as well, a plus. Yeah, there. Now they told me to substitute x equal 1/10 or 0.1. So I'm curious as to how much significance each of the terms would have applied. I don't think I need up to the x to the 7, but no harm having it there. 1 minus, if I substitute x equal 0.1 or 1/10, I get 1 minus 1/10 all to the minus a half is equal to 1 plus 0.1 plus 0.1 squared, which is 0.01, 0.001. I'm missing something here. I'm not sure. What am I missing? I did a bunch of nonsense here. The power is minus a half, buddy. Oh, God. I don't know what in the, it just didn't look right. All right, let me go back. I know there's a better way to erase all this. What in the world did I just do? I'm going to try this again. I'm replacing to expand. One minus x to the minus a half. Replace x with minus x and n with minus a half. So let's see how that goes. I'm gonna go back to my x to the 5th. This becomes 1 minus x to the minus a half is 1 plus minus a half times minus x. The next one is minus a half. Minus a half minus 1 is minus 3 halves over 2 factorial times minus x all squared plus minus a half times minus 3 halves times minus 5 halves over 3 factorial times minus x all cubed. You did a bunch of nonsense here, man. Okay, and then what do I need here? I'll take the other two terms, plus minus a half times minus 3 halves times minus 7 halves, 5 halves times minus 7 halves upon 4 factorial times minus x to the fourth. And then the last one is minus a half times minus 3 halves times minus 5 halves times minus 7 halves times minus 9 halves upon 5 factorial times x to the fifth. I doubt I'll need more than that. If I simplify that, 1 minus x to the minus a half is equal to 1 plus a half x. That's a plus and that's a plus. 3/8 x squared. Determine x cubed would be plus that's, let me see, minus and minus and a minus and a minus gives me a plus. That's 3 times 5 on top, and this is 8 times 3 by 2 by 1. 5/16 plus 5/16 x cubed. Let me take one more term. Take both of them. Next one is 2 2 4 2 0 2 16. Minus 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 minus, that's a plus. This is 3 by 5 by 7 over 16 times 4 factorial, which is 4 by 3 by 2 by 1. Threes will go. 35 upon 16, 264, 128. 35 upon 128. X to the fourth. And then the last one, is that's a plus as well. 3 by 5 by 7 by 9. 2 2 4 2 0 2 16 2 32. And this should have been minus x all to the fifth. Five factorial. It's 5 by 4 by 3 by 2 by 1. 3 5 goes up with 3 and 5. 7 9s is 63. 32 64 128 256 over 256 x to the fifth. Y'all can double check that algebra for sure. I want to wrap this up in less than 5 minutes. This video has been going for a while. All right, so let's see. When x is equal to 1/10, that's 1 minus 1/10, which is 9/10 to the minus a half, is equal to 1 plus a half times 0.1 plus 3/8 times 0.1 squared plus 5/16. 0.1 cubed, 35 upon 128. 0.1 to the fourth, and 63 over 256. 0.1 to the fifth. Okay, 9/10 to the minus a half is 10/9 to the half. Y'all should know that. This is I want to write out each term individually. 1 plus half of 0.1 is 0.05, 0.1 squared times 3 divided by 8. This is plus 0.00375. 0.1 cubed .001 times 5 divided by 16. This is 0.0003125 plus 0.1 to the fourth times 35 over 128. This is 0.1234. 0.00027,343 plus, and then 0.1 to the fifth times 63 divided by 256. This is 0.123450,246. Okay. I don't know if that 2 at the end there is going to add any significance, but let's see. 256. So, 1 plus 0.05 plus 0.00375 plus 0.0003125 plus 1, 2, 3, 4, 7, 3, 4, 3 plus 246. Yes, 10/9 to the half becomes root 10 upon 3. And that's equal to, approximately equal to 0.00. Can't be that, man. It has to be 1 point something. Yes, this is 1.054092303. Root 10 is therefore approximately equal to 3.162276, or if you wanted to, 6 significant figures, 3.16228. Oh, I'm gonna stop this video right here. 3:48, 6. So now in 12 minutes. Too long. All right, the worksheet. It's there. Let's see. This is the first 4 problems. Let's see. Got a snapshot there, and then number 5 on its own. All right, that's it. I'm out.